Class, you might have gotten both the assignments, tree assignment 1 and tree assignment 2, or only one you have gotten.
Only one.
Okay. I will ask them to put the tree assignment 2 also. I have published both of them together. I have to check. Okay. So I might publish the second one too. Then also they will publish. Cool. Now, okay, let's dive into the today's topic. Let's start our discussion. In the last class, we have discussed about the binary tree, which is a non-linear data structure. In the binary tree, what we have discussed about that how the non-linear accessing of the elements can improve the searching complexity. Binary tree itself doesn't improve the searching complexity. The searching in binary tree remains as order of n only. But when we put some restriction on the binary tree, or so if we talk about the variance of the binary tree, then what happens is the searching complexity improves. So one of the restriction or one of the variants of the binary tree is called as binary search tree. In the binary search tree, what happens is whenever all the elements on the left hand side is smaller than the current element, all the elements on the right hand side is greater than the current element. So that's the thing. So because of this restriction, you achieve the searching in order of log n. So that's improve the searching complexity. Now, uh, still because of the skew tree, the worst case complexity of searching in the binary search tree is order of n only. But there are the certain other what I say variants present which can still improve the complexity to versus complexity to order of log n. That is one of them is ABL tree or height balance tree that we will discuss later. Now, today we are going to discuss about an advanced data structure which helps us into a certain situation. Okay, so when we talk about the priority queue or also called as heap, what happens is there are certain before going into this data structure, I want to talk about the scenarios. There are the certain scenarios where you want to have the minimum element or the maximum element every time. Okay, suppose a stream of integers is coming in and somebody asks you to write a query that you should have a minimum or the maximum element every time. So normally how you calculate the minimum element or maximum element? You have, if you have a, look, let's start talking from the fixed array. Okay, so suppose you have a fixed array. Okay, fixed array means fixed size array. So what happens in the fixed size array? Like 4, 3, 1, 2, 5, and 6. Suppose somebody asks you to find the minimum element. What is the complexity of that? Minimum or maximum element? Order of n. Am I correct? So because you have to go through all the other elements and you have to check, compare what is the minimum element against your what is the minimum element earlier. Right. Let's suppose if I told you instead of a fixed array, what you have to do? You have a stream of integers coming in. You have stream of integers coming in. What is the difference? What is a stream of integers? Stream of integers means continuously integers are coming. You don't know what will be the fixes. What you will do? What will be the complexity of this? If somebody asks you at any point of time to write a query to get to write a query to get maximum slash minimum, what will be how you write a query? The problem is simple. Suppose you have a stream of integers coming in, you have to write a query to get the maximum or minimum. First question is how you will write this query. What will be your thought process, or what will be the logic, or what will be the approach?
So it will be like whatever numbers we have, we will be every time we will be calculating the minimum and maximum from that. So
Yeah.
suppose if we got first 10 numbers, from that we will calculate in O of n. Then suppose in the next time we got another number, then again we will calculate with those 11 elements.
Okay. First of all, is my question clear to all of you? Pritam, Raju, Jayan, Gopal, Asmita.
So,
Is question
Vishal
clear?
sir, the stream of integers coming in means that when we get those integers, we store them somewhere, right?
No, you can't store them. See, you can store them. It's up to you how you want to keep it. So stream of integers is like, suppose 4 comes in, then 3 comes in, then 1 comes in, then 2 comes in. So one by one elements are coming in. You don't know how many elements can come in. Don't you think that how you have done it in the fixed array, the same thing can be applied here? Again, is the problem statement clear? Jayant, Gopal, Asmita, Ashwini. Query means a function. Function to get the maximum or minimum. Ashmita, Ashwini. Guys, do you have doubt here or is this clear?
Clear, Nishan. Yes, clear, Nishan.
So what we can do is, it's simple. We can keep a variable. Let's say I have a variable called min. So as soon as the first element comes in, I will initialize min with 4. Now when the next element comes in, I will just compare it with whatever I have in the minimum. I will put it 3. The next element, I will compare. The minimum is 1 now. Okay. Now 2 comes in. We don't do anything. We keep it 1. Okay. Like that. So whenever you have a stream of integers coming in, if you have to maintain the minimum or the maximum, we can just maintain a variable and check it against the incoming element. It's simple as that. The complexity of doing that is order of n. So order of n is the complexity of getting the maximum or minimum, okay, for a stream of integer in order of 1 complex. That's simple. But there is a problem. If in this stream of integers, there another functions return which manipulate this stream, means whatever the elements they have stored, they can take it out or they can put it in. Okay, they can take it out. Suppose there's an additional query return to delete element. Okay, and then you have the query to get maximum. Then what happens is, it means that you have a elements coming in 4, 3, 1, 2, and so on. So 4 comes in, minimum is 4. Okay, 3 comes in, minimum is 3. Now what happens? Somebody decided to delete 3. Okay, so the minimum should reset to 4. Okay, but the problem is we don't have 4 stored. We don't. So that's an issue. The complexity here itself is order of n, but the maximum and minimum complexity is now not as simple as that as compared to the first one, because we have the additional query rules. Okay. So the crux of all of this thing is we need a spatial data structure which help us to get the maximum or minimum in order 1 in for every scenario. Okay, we need a data structure to support get min slash get maximum. Okay, we need a data structure to support get minimum or get maximum in order of 1 complexity in all scenarios, whatever it happens. Okay, so Such data structures, we take the help of priority queue or heap. So priority queue or heap always help us to get the minimum or the maximum in order of the complexity. That is not only the scenario. Okay. There are the another things also. For example, suppose somebody asks you to maintain the top 10 elements or top K elements. Top K elements could be anything. Condition could be anything. For example, you have to maintain top 10 players whose score is highest. You have to maintain the top 10 players who has the minimum score. You have to maintain the top 10 stocks which traded at high volume. You have to maintain top 10 stocks whose stock price is the high. Okay, so that is something also can be solved with the help of the priority queue. So both the scenarios can be solved with the help of priority queue. Top K again, it is not the one-time effort. The data set is continuously changing. So suppose you have certain stocks in the top K right now, but after a day, some of the stocks go out, some of the stocks come in. Okay, so all these scenarios are handled by the priority queue. Whenever we have to find the minimum element and the maximum element n number of times or every times, we can directly apply the priority queue or the heap. Whenever we have to find the top K elements, third largest element. Similarly, another situation is kth largest element or smallest element. Okay, this is also one of the scenarios. So in this also, the priority is going to help. How it is going to help? That I am going to tell you. Today I have to speak a lot. Okay, we have to what exactly the priority queue is, tell how it is got implemented and what are the different different functions it have. Okay, now going to the priority queue. Before going to the priority queue, as I told you that priority queue is a advanced data structure. Okay, priority queue is a advanced data structure. So what happens in the advanced data structure is, from now on, for every advanced data structure, first we are going to define it. Then we are going to write some small utility functions which plays around the priority queue, which plays around the advanced data structure. So every advanced data structure is going to be constructed by using some basic data structures. The basic data structure which we have talked so far are the array, linked list, trees. Okay, so priority queue is going to be implemented by one of this. Okay, then we are going to write the utility function around it to help to achieve the end goal of the priority queue. Okay. Are we good so far?
Yes, sir, got it.
Okay, guys, you can have a thumbs up emoji for me if you are clear, because we have a long way to go in the discussion. Okay, guys, give me a minute. I will look back. And guys, priority queue is a very simple topic, but the complexity part is little bit tricky. The implementation is also very simple. What I want from you guys is, at any point of time, if you feel uncomfortable what I am saying, or if something is not clear to you, please let me know. I can repeat a number of times, but it should be clear to you before going ahead, because everything is connected here. Okay, that is the most important thing. Now, okay, okay, coming to the priority. Another important thing with the priority queue is, it is it is visualizes as a tree. It is visualizes tree, but implemented as array. Okay, it will be more clear when we will go to the further discussion. Give me a minute. Okay. So what I was saying that priority queue is visualized as a tree and implemented as an array. It will be more clear when we will go deep down when we do deep into the discussion. Priority queue, or better to say heap. I'm going to pronounce it a heap. Both are the same thing, just the name differences there. There are two types. One is max heap, one is mean heap. Similarly, you have the priority queue called as the ascending priority queue or the descending priority queue. When you say ascending priority queue or the descending priority queue, okay. So in the ascending priority queue, the smallest key or the element will have the highest priority, or descending priority queue, the biggest element have the highest priority. Why it is called as queue? Queue is a data structure concept in which you follow first in, first out. Okay. You follow first in, first out. What does that mean? Is suppose you have the elements like 4, 3, 1, 2 to process. You put the element 4, 3, 1, and 2. So whatever the element you have put it first will go out first. It means that the element which you have put it first is the highest priority. Okay. So I will write it like P1. Then the second element which you put it, that is the second priority, second highest priority, third highest, and the fourth highest priority. So what happens is whatever the highest priority that goes out. Okay. So this is the case. As you put the element in the queue, the element got the priority. The element which you put it first is the highest priority element, so that's got out. Okay. Now what happens in the priority queue is you assign the priority based on the which is the smallest. Okay. So the smallest in this queue is P1. So I will assign the priority 1 to this, priority 2 to this, priority 3 to this, the priority 4 to this. Okay. So the highest priority is P1, then P2, then P3, and then P4. Okay, so this P1 is the highest priority. So the one will get out first, then the second will go out, then the third will go out, and then the fourth will go down. So that's why it is what is it is? It is the ascending priority queue. Okay. Then descending priority queue. Descending priority queue is we will assign the priority, highest priority to the highest element in the queue. Which is the highest element here? 4. So my priority P1 will be assigned to 4, then P2, P4, P3. Okay. So 4 will be the first one to go out, then 3 will be go out, then 2, then 1 will, then 2 will be go out, and then eventually 1 will go out. Okay. So the highest element will have the highest priority. That is the descending priority. Okay. The same thing is we call as max dependent mean. Now let's talk about the most important part. Are we clear so far? What do we mean by ascending priority queue? What does the priority queue stands for? Okay, is this clear? Any doubt here? Okay. Now, yeah, let's talk about this more. Okay. Max heap or mean heap follow certain rules. Heap follows certain rules. Okay, listen to the rules very carefully. Why? The heap, so that the heap property should be maintained. These are the certain rules which a heap need to follow. First rule, okay. Root value is either smaller or greater than the its children. Then left child, left and right child. Okay. Most important part is I have just written left child and right child, not all the nodes. So that's the clear difference between the binary search tree and the heap is root value is either smaller or greater than both the left child and the right child. Okay, that's it. So it means that if I construct a heap, it looks like this. 5, 4, 3, 2, and 1. This is a heap. You can check at every node. What happens? Your root node is greater than the left child and the right child. 5, it is greater than 4 and 3. 4, it is greater than 2 and 1. Okay. Second is always the insertion happens from always insertion happens from left to right. Always the insertion happens from left to right. So for example, if you want to, let's suppose this is hypothetically, let me modify this string so that we can include further numbers. Suppose this is 9, this is 8, this is 7, this is 6 and 5. Okay. This is also match. Now, suppose I want to insert 4. So 4 will be inserted to the left to right manner. Left to right. It means that whatever the first available space, first available address there in left to right manner, there it will be inserted like this. Okay. We will certify the other heap property later, but the insertion always happens from left to right. That's what it means. It shouldn't be like that. You have inserted 4 here. Okay, that is wrong. Always it is filling from left to right. Okay. Are we clear on this?
Yes.
Rajan, Raju. Another thing is this is second property. Third property says that if you do sequencing, if you put sequence number, if you put sequence number left to right, level by level, no number should be missed. No number should be missed. For example, suppose this is the tree. What does it means by suppose I have to start putting some numbers starting from 0. 0 is there, 1, 2. I am going level by level, and that too left to right while putting the numbers. Then 3 and then 4. It is completely fine. Then what should I mean by missing? Okay, let's see that example. Now, suppose 7 will have another children called 4. This is satisfying your first rule, not second. That's about third rule. So you have 0, 1, 2, 3, 4, and this empty address also you will count there, and then you have 6. It means that the sequence number 5 is missing. You have not saved anything at sequence number 5. Okay, so that's an issue. That is what I meant by missing. So if anything is missed, means any address is missed in between, that is not acceptable. Okay, the sequence number should not be missed. So I will put the sequence number to the missed element also. Okay, there should not be an element. It is not there, so that's why I'm calling it as a missed element. Okay, so there should not be any missed element. Then the fourth is all leaf node should be at level L or L minus. Only all leaf node should be at level L or L minus 1. Means the last level and the second last level. What does it mean is what does it means is suppose for 6 you can have 4, you can have 2 and 1 here. Definitely it is not satisfying your second property, third property, but just hypothetically for going to the fourth property. Leaf node, this is level L, this is L minus 1 and this is L minus 2. You can see that the leaf nodes are at present at L also, L minus 1 also, and L minus 2 also. That is not acceptable. All the leaf nodes should be at L or L minus 1. Okay, so these are the 4 properties which are quite important while solving them. Any element which does not satisfy this heap property or void the heap property, what we need to do, we need to perform certain operations to maintain the heap properties. Okay, so that operations are called as Amplify Operation. That will be more clear when we go into the discussion. Are we clear so far? Any doubt at any point which I just made? Asmita, Ashwini, Gopal, Jain. Ashwini and Asmita.
Nishant, could you please explain last rule once again?
Sure. Last rule says that all the leaf nodes. Okay, if you put the level here. Okay, so this is level 0, this is level 1, this is level 2, and this is level 3. What happens here is where the leaf nodes are there at level 3, at level 2, and at level 1. So 3 and 2 are the only acceptable values for the leaf node to present, not the 1. Okay. So that's what the fourth point says, that all leaf nodes should be at level L or L minus 1. Okay. That's what it means. This is L, this is L minus 1, and this is L minus 2. That's why it's not a. If it is constructed like this, it's this is a heap. Why? Because if you look around, this is the level 2, this is the level 1. Okay. This is the level 0. So where your leaf nodes are at 2 and 1, that is acceptable because leaf node at L and L minus 1 are acceptable. Okay. That's the whole thing. Hope is it clear now?
Yes, got it.
Okay. Now we know what the heap is. Okay. So let's take an example of max heap and mean heap. So there is a clear difference between the your BST and the heap. BST is all about all the nodes in the left hand side and all the nodes in the right hand side. It is all about the left child and the right child. If I create a, this is a max heap, by the way, because every value is greater than its left child and right child. If we talk about mean, one is there, then we can have 3, we can have 2, we can have 5, 4, 6, 7. This is a example of a mean heap. Every element is smaller than its left child and the right child. Cool. Let's move forward. So before going ahead, we'll see how we are going to implement it. So this is how visualize it. As I told you that visualization is going to happen as a tree, but the implementation is going to have it as an array. So what happens here is this is tree we have visualized it, but because of all this property, we will be able to save it in a array. So I can give the sequence number like this: 1, 2, 3, 4, 5, and 6. And based on the sequence number, same way we can store it in a array. And why we are able to store it in an array in a proper manner? Because of the property which we have just discussed about. So let's so you have 1, 3, 2, 5, 4, 6, and 7. 1, 3, 2, 5, 4, and 6. So if you look at the indexes, it is 0, 1, 2, 3, 4, 5, and 6. Okay. So this is how it is going to be implemented. And why we are able to use the array? Because of the because of these properties. Nobody asked me why you have used an array instead of a linked list. Why? Why we use an array here? Anyone why we have used an array here? What the advantage array is going to give? The array gives the advantage of direct addressing. That's why the implementation is based on array, because array gives you the advantage of direct addressing. Okay. If I have to declare a class, if I have to implement a heap, let's see how we are going to do the implementation. Then it will be more clear why we have used an array. So suppose I can create a class. Let's say heap. In my class, what I need few things. How? I'm going to tell what is the current number of elements. Current number of elements. I'm just going to tell the current number of elements. Then capacity. Capacity to the total number of elements it can have. Since we have used an array, okay, so array needs to be of fixed size. So you can define a heap of size 100, but you can use 10 elements into it. So that 10 elements will make the count and the 100 will make the capacity. Okay. Then you have array, okay, define, declare. Then you are using a enum or an integer to tell you what is the heap type, whether it's a max heap or min. This is how I define the class. Now, as I told you that once we have the heap defined, we are going to write some utility functions to support this heap. Okay. Now, there are the different. So one is you can have the constructor here within the class to take the capacity and give you the object of the heap. Okay, that I am not done, but you can have a constructor like heap and capacity and heap type. Okay, and then polygon into dot capacity equals to capacity dot data. Now, yeah, are we good so far? Surgeon, Pritam, Jayan, Rashmini, Rashmita. Cool. Now, utility functions. What are the different utility functions I'm talking about? What are the utility functions? First utility function is to find the parent. I called as find parent. So what does it mean is, suppose you are at index I. Okay. So let me create a heap here. Heap here. So let's create a maxi pointer. Suppose let's start with 7. You have 3 here, you have 6 here, you have 5 here, you have 4 here, you have 2 here, you have 1. This is a maxim given to you. And this maxim, suppose you are at, and how this maxim is going to store it in an array. So if I put the sequencing, it will be 1, 2, 3, 4, 5, and 6. Right. So the sequencing in the array, it is going to store like this, where you have 7, 6, 3, 7, 6, 3, 5, 4, 2, 5, 4, 2, 1. Okay. So this is how they are going to store it in the array. Okay. So indexing will be 0, 1, 2, 3, 4, 5, and 6. Okay. Now, suppose if I ask you that, if I ask that you are at index here, what is the parent of this? Means, what is the parent of value 4? What is the parent of this 4? Okay, at what index the parent of this 4? Okay, let's give it. Yeah. So, suppose if I ask you that what is the parent of index I, then what it should be? So the parent of index I or parent of 4. The parent of 4 is clearly 6. It is at index. But what should be the calculation should look like?
2 into I plus 1, 2 into I plus 2.
Let everybody think. Okay, if you have something, put it in a chat. Let everybody think. If you are at index I, if I ask you at what index your parent should be, then what it should, what index it, how you calculate that index. Is the problem statement clear? Anyone is having doubt in the problem statement? Okay. What I meant is, suppose if I ask you what is the parent of index I, so index I suppose is equals to 4. I is equals to 4. So the parent of I is at index 6. Okay. This is an index 1, sorry. Index 1. How I need the calculation, how you can calculate the parent for an index. That's my question. Okay. Before going to this, can you tell me for an index what is the left child, where the left child should be? If I is an index, where the left child should be, and where should be the right child of this index? So, for example, index 2, the left child is at index 5 and right child is at index 6. How you can calculate the left child and the right child for a particular index? Okay. First, let's calculate this, and then we'll move to the parent. How you can calculate this? Okay. So I will help here. If you are at index I, the left child will be at 2i plus 1. And right child will be at 2i plus 2. Apply any index. If I is equals to 2, it will be 5 and it will be 6. If I is equals to 0, it will be 1 and 2. If I will be, let's suppose 3, it will be your 7 and 8. Okay. So that is the thing. So if you are at index I, the left child will be at 2i plus 1 and the right child will be at 2i plus 2. Is this clear? Ashmita, Ashwini, Pritam.
Yes, Nishant.
Now, looking at I, again, what should be the parent? Opposite thing. If you are at index I, what will be the parent of I? Yeah, so it will be I minus 1 by 2. I minus 1 by 2. So I minus 1 by 2 is sufficient for both the left child and the right child to get its parent, because in all the language calculation, this is the floor. So mathematics supports two functions. One is called as ceil and one is called as floor. So ceil means you round off to next integer, means 2.3 will be 3, 2.3 will be 2 in the case of floor. So by default itself, the integers do the round off to the floor only. Okay. So that's what. So let's try to apply. So suppose you are at 5. What will be the parent? 5 minus 1 by 2. So that will be 2. What about 6? 6 minus 1 by 2 is 5 by 2. That is 2.5 and eventually it becomes 2 only. So that's the case. So the parent will be at 2, 5 will be at 2 and 6 will be at 2. Okay. So that is the case. Now, how will write it into the code? So we have to write the utility code. Guys, one more important thing is, before going ahead, I told you while defining the class itself that we have capacity and count. Okay. So suppose you have defined an array of certain capacity. Okay, like this. So this is your array of certain capacity. Okay. Now let's say it is starting from 0. 0, 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so the total capacity is 11. Now let's suppose total count is 5. Okay, so we will be using this total count, this count to represent the boundary within the array. When I say the boundary within the array, a boundary of heap will be the eligible elements to be considered inside element. Boundary means eligible elements inside heap. Outside this boundary, we will not be consider the element, or we will bother about them. So for example, if the count is 5, that count is represented here. So that is the value of h count minus 1. Okay, because the indexing is started with 0. So if your count is 5, this is represented by h count minus 1. All the elements after this I am not bothered about. I am bothered about all the elements from 0 to h count minus 2. Okay. If I insert one more element, this h count will become 6. So it will be represented by the index 5. If it is decreased, it will be represented by index 3. Okay. So this h count is going to help me to create the boundary. So boundary will be from 0 to h count minus 1. This will be the boundary. Okay. All the elements outside this boundary is not eligible to be considered within the heap. Okay. Are we good? Now let's let's quickly write the function for the parent. Okay. So I will be returning int. I will have a function parent. I'm taking an index. I am taking a heap. Oh. Now, first, I need to check whether this is a valid index or not. Means it should be in the boundary. So if I is less than 0 or I is greater than h count minus 1. Okay, if I is greater than h count minus 1, then we will be returning minus 1 to represent no parent because this is not a valid index. Otherwise, what we will do, we will return I minus 1 by 2. That will give the index for the parent. Okay. Are we good? Now, another thing, another utility function is left child and the right child. So find okay, find right child. Okay. Find left child. Left child will be here again. Let's write a quickly write a code. So for left child, I already have a code. I think that can help us. So this is a C code. I can just quickly convert it into a Java code. This is class heap. We have I, index I. We have calculated the left, and we will just checking whether the left is outside the h count. If it is equal or greater than h count, it will return minus 1. Then we will return the left. Similarly, we have the right child. Okay. And again, we will be checking if the right is. So these are the few utility functions we have written. Are we clear? Asmita, Ashwini, Jayant, Pritam.
Yes.
Anyone is having any doubt so far? Now, another function is getting the maximum value and getting the minimum value. So getting the maximum value, just tell me in the max heap, where will be the maximum value lie? In max heap, where the maximum value will lie?
In a root.
In the root. And where the root is?
Right index.
It is 0th index. Okay. So if you have to get the maximum value in the max heap, you will always have at the root. Okay, so you have a heap. The count need to be positive, or the h count need to be greater than 0 for this. If it is less than equals to 0, or if it is equals to 0, then you will return -1, otherwise you will be returning the 0th index element. Okay, to getting the maximum. Similarly, the minimum value in the min heap will be again at the root only. Like this. Cool. Now, tell me one thing. Are we good so far? Getting the maximum value and minimum value, it is always at the root, which is represented by the 0th index. What is the complexity of this utility functions? Finding the parent, finding the left child, right child, getting the maximum value or the minimum value. What is the complexity of this? Cool. Okay, it is order of 1 only, because what we are doing, we are just doing the index calculation. So getting the minimum value, maximum value, right child and the left child are always the order of 1. All these are the order of 1. Okay. So remember that, because now we are going to see something more about this in the utility functions. Okay. Next utility function is called amplifying operation. I told earlier also, suppose in the heap, if one of the element is not satisfying the heap property, then we have to perform certain operation to maintain the heap properties again for all the elements. Such operations are called as amplify operations. There are two types of amplify operations. One is called as percolate down and one is called as percolate up. What? So I'm going to talk about amplify operations. There are two types of amplify operations. One we call as percolate down and one we call as percolate up. Okay, percolate down and we have percolate up. Right now we are going to talk about the percolate down. Percolate up, we will see after some time. Now, let's suppose you know the heap and you know the index at which the heap property is not satisfied. Suppose we have a max heap. Let's take some bigger max heap, like 12, 10, 11, 4, 3, 4, let's take 6, 9, 8, 7, 5, 4, 3, 2, and 1. This is a max heap. First check it is a max heap or not. Everybody, please check whether it's a max heap or not. A max heap? Okay. Now suppose in this, one of the properties is not satisfied. So in this max heap, what I will do is, let's suppose in this 10, in the place of 10, we have 0. Okay. In the place of 10, we have 0. Now, what happens? Is this a max heap? No. We know that at this position, the heap property is not satisfied. Okay. At this position, heap property is not satisfied. Everybody listen to me very carefully. How we can satisfy the heap property again? That operation is called as amplify, and particularly we are going to do the percolate down. What I am going to do is, I am going to compare this current element with the left child and the right child. Okay, and see whoever is the maximum. I will replace this element with the maximum element. So among 0, 6 and 9, the maximum element is 9. So I will replace swap 0 and 9. Now, my current element changes from this to this position. Again, I will be comparing 0, 3, 2. Who is the maximum? 3 is the maximum. So I will be swapping 3 and 0. Now you can see that we have reached the leaf node. It means that we have amplified the heap again. Now you can see that all the elements are satisfying the heap property. So it means that in percolate down, we are going to compare with the child nodes. Compare with child nodes. Okay. Now, in percolate down, either you should reach the leaf node or either it should be hippify in between. So in between, if how you should know that it is hippify in between, because whenever you try to get the maximum of all these three elements, if you get the current element as the maximum element, it means that you have hippify the whole path. So you don't have to go down. Cool. Okay. So either while hippifying, now hippifying operation, we need to consider continuously is a continuous operation. Means it is not like a one-time operation. Once you apply it at this position, it means then you have to apply it to this position also till all the complete path is hippified on it. Okay. So either you reach the leaf node, either it is hippified within the path itself. How you come to know that whether it is hippified in the path or not? Your current, when you try to find the maximum of all three elements, it will come out that the current element is the maximum element. That's how you come to know that. Okay, so that's how you do the Happify operation. Is it clear? Okay, are we good? Sajan, Raju, Pritam, Asmita, Ashwini, are you good? So this is going to be a recursive function. Okay, so whenever you swap an element, you have to call the same function on the new index also for where you have swapped it. Okay. Asmita, Ashwini, Pritam. Cool. Guys, can you try to write a code for this? So I will be helping out you with the function signature. So suppose you have this void, so pull it down. Okay. We have given a e, h, and a int I, where the heap property is not satisfied. You have to complete this. Okay. I'm going to write the code for this. Okay, just follow me. Okay. So here one thing is predefined that we know the index of the element which is not satisfying the heap property or which violates the heap property. Okay. Now we don't have to search for that. Okay. And how it's going to help us, that I will let you know. So suppose I'm taking two variables in max and in time. I'm taking the left side uh, left child into the LC where in the variable LC, and I'm calling the function left child, which we have already written, passing the h comma I. Okay. Similarly, I have another, yeah, I will be calling a right child into the RC. Now we have. Now I will be checking which one among these three current LC and RC, which one is greater. So if my LC is not equals to -1, means it is in the boundary. Okay, it is not equals to -1. And H dot array of I is uh, smaller than H dot array of LC. Okay. So this is the case. It means that your left children is greater than your current element. So max is equals to I. Max is equals to LC. Else, if this is not the case, then what I will be doing, max is equals to the current element. is high. Now we have made a comparison between the left hand and the current trend. Now we have to make the comparison between the uh, right trend and the maximum value. Okay, this is how we are going to check. So if RC is not equals to -1 and so, and if RC is greater than the maximum value, max, whatever the max hold the index. Okay, the maximum then the maximum value, then the maximum will hold the RC. LC, RC, and R this, all these are the indexes. Okay. Now, what we will do, we will check whether the maximum is the current element or not. So if maximum is not equals to the current element, then we will swap the current element with the maximum element. And again, we will call the percolate down on the maximum element. So this max element is nothing but the index. Okay, like that. So this is how here we are doing the comparison number 3, and we will be checking if maximum is not equals to the current element. If maximum equals to the current element, it means that it is already amplified. Okay, that is it. So if it is not, then we will swap both of them, both the elements, and we will call the percolate down on the maximum element. Okay, guys, is it clear? Ashwini, Asmita, Jayam, Pritam, Raju, Pritam. Asmita and Ashwini, is it clear now? The problem which you guys are facing. Can anyone help me out? What will be the complexity of this operation, percolate down operation, and why it is called percolate down? Because we do the comparison with the child elements. That's why it's called the percolate down. When we are going to learn about the percolate up, you will see that we will be doing the comparison with the parent. Okay. So are we good? So can anyone help me out with what will be the complexity of this?
Order of height of the tree, I guess, because it will percolate down till the leaf.
Yes, that is correct. It is equal. The complexity here is, and it is very important to understand. So, time complexity here is order of log n. Log n is height of the tree. Okay, log n is height of the tree. Because you will be choosing among left and right only single thing. Okay, so you will be following a path till the leaf node. So that will be equals to the height of the tree. That's why the complexity is log n. Okay. Smita, Ashwini, Jayan, Pritam, Raju, Sachin. Okay. So today I'm going to stop here. Okay. Tomorrow we are going to look more than this. Tomorrow what I want is you guys to go to the recording again. Try to grab the things which we have discussed so far, because tomorrow the things going to be a little bit more complex. Okay. So please come uh, before attending the tomorrow's class. Please go through the recording again, and then we will continue our discussion for the priority queue and the heap. Are we good?
Yeah.
Thanks, Nisha.
And tomorrow's timing is 9 o'clock. I will communicate on the channel right away. Just a minute.